Hello everyone, today I will show you a problem from the 2009 International Maths Olympiad. This was the fifth problem out of the 6 total problems, which were to be done in 2 days. Referring to the difficulty list in the description, this problem is rated at around an 8. Without further ado, let us get into the problem. Let Px be a polynomial of degree n greater than 1 with integer coefficients, and let k be a positive integer. Consider the polynomial qx equals p applied to p applied over and over k times. Prove that there are at most n integers t, such that qt equals t. So essentially it is asking us to prove that there are at most n distinct integer solutions to the equation qt equals t. So first we write qx as p to the power of p to the power of kx for ease of notation. So our first idea is we might try induction on k, because if we prove that x is a solution to p to the power of kx equals x, then x must also be a solution to p to the power of k minus 1x equals x, and then we can iterate this until we have that every solution to p to the power of kx equals x must also be a solution to px equals x, which would mean that there would be at most n solutions, because p is at most degree n. How might we go about this? Contradiction. Suppose t is a solution to p to the power of kx equals x, but not a solution to p to the power of k minus 1x equals x. Unfortunately, there aren't any good ways to continue from here. What we're missing is an important condition in the question, that the polynomial has integer coefficients. There are many lemmas associated with integer coefficient polynomials, and the problem is begging for us to use them. Here's an important lemma in integer coefficient polynomial problems. Any solution to p to the power of kx equals x must also be a solution to p applied to p x equals x. So here is how we are going to prove it. The major lemma that we are going to use is that a minus b divides pa minus pb. This is easy to prove. The main idea would be to use the lemma to create a chain of divisors. This way we can fully utilize the integer property of the polynomial. So how are we going to create the chain of divisors? Well, px minus x divides px minus px divides divides p to the power of k plus 1x minus p to the power of kx, which, using the condition in the problem, equals px minus x. How does this work? Well, we simply keep swapping out the a in the lemma, replacing a with pa and b with pb, and so on. Now, if each part is 0, then we can deduce that px minus x equals 0, which in turn implies that px equals x, and which implies p applied to px is equal to x, and the lemma is proven. Otherwise, given that x is a solution to p to the power of kx equals x, the sum of all the parts of the divisor chain must be 0. So if we just look at the divisor chain and add them up, we can see that, for example, px appears twice, once in its positive form and once in its negative form. And if we add them up, we will get p to the power of kx minus x equals 0, which means that p to the power of kx equals x. Then, since no part is of the divisor chain, no section of the divisor chain is 0, then there must exist some integer a such that p to the power of ax minus p to the power of a minus 1x is equal to negative bracket p to the power of a plus 1x minus p to the power of a x. And after simplifying this expression, we have p to the power of a minus 1x is equal to p to the power of a plus 1x. So we are almost done here with this lemma after we reach this step. Now we can simply continue to replace the a minus 1 with a plus 1 in the above equation and use the fact that p to the power of k x is equal to x. Then eventually we will get the result p applied to px is equal to x, and so this lemma is proven. Finally, note that if k equals 1, then we have px equals x, and after applying p to both sides, we have p applied to px is equal to px, which is equal to x, and we are done. Now back to the problem. So we have now proven the lemma. We will try to use the lemma. First, suppose the contrary, that there are at least n plus 1 distinct integers t such that qt equals t. Then let R be the complete set of solutions to p to the power of kx equals x. This means that the set R can have at most n. This means that the set R has at least n plus 1 elements. So let R be any element in capital R such that which is a solution to p to the power of kx equals x. If for all elements in R, PR equals R, then the number of elements in R is less than or equal to n, which is a contradiction. Otherwise, there exists some s in R such that PS does not equal to S. Then again, using the fact that A minus B divides PA minus PB, we can produce the following chain of divisibilities. R minus S divides PR minus PS, divides PR minus PPS equals R minus S by our lemma. This in turn implies that all the values in the divisibility chain must be equal, so absolute values R minus S is equal to absolute value of PR minus PS. Now R minus PS divides PR minus P applied to PS, which equals to PR minus S by our lemma above, which divides P applied to PR minus PS equals R minus PS, again by our lemma above. This again implies that all parts in the divisibility chain must be equal, and so R minus the absolute value of R minus PS is equal to the absolute value of PR minus S. Now we use the above two equations that have been generated, and suppose for now that none of the parts in the chains is 0. Case 1. Suppose R minus S equals PR minus PS from I. Rearranging this equation, we have PR minus R equals PS minus S. Call this equation 3. From 2, if R minus PS equals PR minus S, then we can, after rearranging, we get PR minus R equals S minus PS. Compare this to equation 3. We get PS equals S, contradicting the definition of S, because PS does not equal to S. Otherwise, we have PR minus PS equals S minus PR. Rearranging, we get PR plus R equals PS plus S. And then after combining with 3, we get R equals S. For now, this contradicts our supposition that no part of the divisibility chain is 0. Case 2. Suppose, from the first equation, suppose that R minus S equals PS minus PR. Then after rearranging, we get PR plus R equals PS plus S. Keep this equation handy. We will be using it later. So therefore, we can conclude that for all solutions R such that no part of the divisibility chain is 0, PR plus R equals PS plus S. Now we will try and tackle the cases where part of the divisibility chain is actually 0. If R equals S, then PR plus R is clearly equal to PS plus S. If PR equals PS, but R doesn't equal to S, then P applied to PR equals R equals P applied to PS equals S, a contradiction because R does not equal to S. Finally, if PR equals S, then applying P to both sides, we get P applied to PR equals PS, but again using the lemma, we have that P applied to PR is actually equal to R. Therefore, PS equals R, and therefore PR plus R equals S plus PS equals PS plus S. Why is the equation PR plus R equals PS plus S so important? Because since all solutions in the set of solutions R to P to the power of Kx equals X must also be solutions to the equation P applied to Px equals X, and the solutions of P applied to Px equals X must also be solutions to the equation PR plus R equals PS plus S, as shown above, where S is a constant. Now, the degree of P is n, and the equation, after rearranging it so that the right hand side is 0, and the left hand side is PR plus R minus C for some constant C, then it follows that the equation, the left hand side of the equation, is a polynomial of degree n. It is known that a polynomial of degree n has at most n solutions, and therefore R, the set of solutions R, must be less than or equal to n, which is a contradiction. Therefore, there are at most n integers t, such that qt equals t, and we are done.